This episode of Big Picture Science is brought to you in part by Upside. Upside finds you the best deals on flights and hotels for business travel. Learn more at upside.com. One thing about exploration, there's no guarantee you'll get a round trip. That was certainly true for the British explorers who trekked across 800 miles of ice to the South Pole, and for many of the sailors who first braved the far reaches of the Pacific. Many simply never returned home. But non-human exploration is almost always a one-way journey. Unless your destination is the moon, being a spacecraft means saying goodbye to your human handlers for good. Although they will remain in touch with you as long as they can from Earth, gratefully receiving the data you so dutifully collect from elsewhere in the solar system. You tell us about icy planetary rings, layer cake mountains, worlds with methane rain and freezing lakes, and for that, we're grateful. But to you, the spacecraft, we have to say adieu. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology, and in this episode, our robots and machines have rocketed to destinations in the solar system where humans have not yet at least, perhaps never. The pioneering flybys of spacecraft such as Voyager and Cassini and touchdowns by landers such as Philae have deeply enriched our understanding of the solar system, how it was formed, and what is out there. But all missions must come to an end, whether by programmed destruction or a slow fade into the cosmic abyss. We'll take a look at the fate and legacy of a few of them. It's Spacecraft Elegy.
Now, I'm not playing solar system favorites, so let me say that right here and now. All of the planets, their moons, even the icy rocks that dart between them, they each have their special charm. I'm talking to you, Pluto lovers. But one might argue that for sheer visual drama, it's hard to beat the second largest planet in our solar system, Saturn.
This gas giant is a thrilling sight viewed from a telescope on Earth, but upon closer inspection, this planet, adorned with thousands of beautiful ringlets and more than 60 orbiting moons, is a showstopper.
NASA's Cassini spacecraft was the first to orbit the Saturnian system, the iconic rings, of course, but also its moons, from moody methane-drenched Titan to geyser-gushing Enceladus. The grand finale of Cassini is coming up, and we'll describe its dramatic end in a moment.
But first, a reminder of the mission's highlights then and now. What follows is an excerpt from our interview with the leader of the Cassini imaging team, Carolyn Porco, back in 2009, not long after the first flyby of Enceladus. We assumed that the small moon was a dormant ice ball in the middle of Saturn's E-ring. Surprise.
Yeah, I would say it has been the biggest surprise, because while we did suspect, even before we got there with Cassini, that there might be some kind of jetting activity because of the E-ring, we never, ever expected it to be as visually spectacular and dramatic as it turned out to be.
You say jetting, and what you mean is some sort of material being shot out, sort of like a geyser out of Enceladus.
I say jets because that's what it looks like. It's material jetting and producing these lots of very narrow jets. But those jets, we think now, are geysers, and geysers carries the very specific definition of erupting from pockets of liquid water. And it's been the thing that points to a very exciting possibility that under the subsurface of the South Pole region on Enceladus, which we know already is giving off excess warmth, has coming out of it water vapor and simple organic compounds. We think there's liquid water as well, in fact, maybe liquid salty water. And so it's just coming together. Over the last few years, we're becoming more and more confident that we very likely do. You know, we scientists, we don't like to commit to anything, definitely, but, you know, it's looking really good that we might have a habitable zone under the surface of Enceladus where at least prebiotic chemistry and maybe even life might be stirring.
In the 7 years since, Cassini has discovered an ocean under the icy crust of Enceladus, and recently that the plume contains an ingredient that could support life, molecular hydrogen. SETI Institute planetary scientist Matt Tiscareno says Enceladus has been one of many stunning scientific successes of Cassini.
So now we have this scenario where there is energy and there are organics and there is liquid water. And we know that they're all in communication with each other. And so that does make Enceladus one of the most interesting, possibly habitable environments in the solar system.
Well, one of the things that has been announced about Enceladus, even with a press conference, which is fairly dramatic, is that Cassini sampled some of the material coming out of Enceladus and found some intriguing composition that kind of hint at the possibility of microbes under all that ice.
Yes, that is the most recent Cassini discovery with regard to the Enceladus plumes, is that they detected trace amounts of hydrogen in the plume, which points to at least some kind of pre-organic chemistry that would make a habitable environment possible. I don't think it proves that microbes are actually present, but I think it does demonstrate that an environment in which microbes could thrive is likely present.
Cassini's been on the job for a long time. When you look back on that 13-year career, what strikes you as some of the most interesting things this plucky little spacecraft, they're always plucky, I'm not quite sure why, this plucky little spacecraft has done? What has it found that you would rank near the top of the list?
Cassini has a laundry list of amazing discoveries that it has made. We've already talked about Enceladus. We could talk for a long time about Titan. We knew practically nothing about the surface of Titan. It was the largest expanse of unexplored real estate in the solar system in 2004 when Cassini arrived. And we now know that it is a landscape with very recognizable features that we know from Earth, including river valleys and lake beds and sand dunes, with the difference being that instead of water flowing through these features, it's liquid hydrocarbons. The kind of natural gas that you burn in your stove is so cold that it liquefies. And what we think of as water is frozen hard as a rock and is actually playing the role of rock on the surface of Titan. And then we would also get to my personal favorite, which is Saturn's rings. We've just discovered an enormous amount of what goes on with this tremendously intricate system that is constantly moving in 100 different ways at the same location at the same time. We've learned about the chemistry, that the ring particles are made up of very fine water ice. We've learned about embedded moonlets that give us a window into the life of baby planets, which also are embedded objects in a disk system. We've been watching how these, we call them propeller moons, these embedded moons, as they change in their orbits because the disk is affecting them. And now with the ring-grazing orbits, we've gotten some close-up looks on the disturbance that they create in the rings. So looking at then both sides of that interaction and just a number of other things.
When we look at the rings, I mean, are we looking at something that's very old? And where did they come from anyhow? When I was a kid, they would tell you at the local planetarium that Saturn's rings were the result of, some moon encountering some sort of disaster that broke it up into all these ring particles. I kind of wonder whether that's still considered a very good idea.
I think it still must have something to do with an object that got too close to Saturn and encountered some sort of disaster. Whether it was a moon of Saturn or whether it was something making a close flyby from an orbit around the sun, I think that is still undetermined. There has also been a new question opened up as to how old the system really is. It's much easier to pull apart a moon into a ring system in the early days of the solar system because the solar system was a much more chaotic place. There were things flying around every which direction. And in the last few billion years, it's become much more orderly. And so it's a lot harder to find a big object that will stray into that dangerous territory and get pulled apart. So for that kind of reason, it's more appealing to think that the rings are probably as old as Saturn. But you run into some problems with that. How do you maintain such pristine water ice over 4 billion years when you're constantly being bombarded with dirty material from the rest of the solar system? The other thing that has more recently come to light through Cassini is if you look at how the orbits of Saturn's moons are changing and you rewind that process backwards, you can only go back for about 100 million years before you start to run into problems. So it may be that not only Saturn's rings, but the entire inner portion of the Saturn system, all of its inner moons, is only about 100 million years old.
Only 100 million years old. That's really remarkable. But now Cassini, the craft that has made this discovery, is about to say goodbye. It's running out of the fuel needed to maneuver. So it's only fitting that the spacecraft's exit is as dramatic as its images of the Saturnian system. During its swan song, it will slip inside the rings before crashing into the planet itself.
The final episode is the grand finale, which will begin in April, where Cassini spacecraft will come over the north pole of the planet and dive in between the rings and the cloud tops of the atmosphere, and will continue doing that through September, about once per week, getting spectacular data each time, and will eventually then, on September 15th, we'll dive into the atmosphere of the planet itself.
Now, if I were on the Cassini spacecraft, I'm not sure I'd want to be at this point, but if I were on the Cassini spacecraft looking out the front, what happens to me?
So if you are on board the Cassini spacecraft as it enters into this final plunge, you would start by seeing the north pole of the planet clear in front of you, and you would have more of a sense that you're moving vertically down onto it. And you would then see the rings off to your right and the planet off to your left, and you would be on a kind of a grazing trajectory, but you would, around the equator region, start to descend through clouds and things like that. And at some point around there, you'd better bail out and pull the ripcord on your parachute before the spacecraft continues plunging so far in that it burns up.
Deploying my parachute, I'm not sure that's really going to help me much, is it?
It's true. A parachute by itself would not help you very much, because you would continue to descend until the atmosphere got so dense and thick that it crushed you. So you would need some kind of airplane or rocket or balloon to pull you back out of that environment.
And that's what's going to happen to Cassini? I mean, just going to be crushed like a soda can?
More or less, yeah. It is in some ways a sad end for this really intrepid robot that we've been traveling with for so long. There's a new video that the Cassini project put out to kind of dramatize what the final plunge will look like. And I will admit, as I looked at it and watched, the bits of fiery gas playing at the edge of Cassini, I got a bit of a lump in my throat to think about how far we've been with this robot, and it's finally going to meet this kind of a fate.
Well, why did NASA condemn it to this? I mean, it was still working. It is still working. Why pull the switch?
Planetary missions do need to have an ending point. There is actually coming a time pretty soon, if Cassini were to stay in orbit around Saturn, where it would no longer really be able to reliably control where it's going. And because it does have fuel on board that it uses for course corrections and for pointing itself and the like. And that is really running on fumes at this point. It's another reason why this has been a tremendous spacecraft that has served us so well. But we really can't expect it to continue that way for very much longer. And if we were to allow it to just stay in orbit around Saturn indefinitely, at some point, who knows, 1 million years into the future, it might crash onto Enceladus, and we really want to avoid any possible contamination of Earth-derived materials from landing on Enceladus, where it might have an independent habitable environment.
Matt Tiscareno, thanks so very much for speaking with us.
Thank you very much for having me.
Matt Tiscareno is a planetary scientist at the SETI Institute.
We say goodbye to the Cassini spacecraft in September, but the discoveries made during this mission have changed our understanding of the Saturnian system. Among these, the composition of its rings and 2 of its especially intriguing moons, Titan, with its hydrocarbon lakes, and Enceladus, whose subterranean ocean may turn out to be one of the most likely places to find life in our solar system.
Saturn is one of the largest objects in the solar system. Up next, visits to 2 of the smallest.
It's Spacecraft Elegy on Big Picture Science. This episode of Big Picture Science is brought to you in part by Upside. Upside is a new way to buy business travel. Buying a trip at Upside saves you money because they bundle your flights and hotel together for maximum cost effectiveness. If you're a frequent business traveler, you can save your company money and increase the rewards you'll receive from Upside. The more money you save, the more Upside rewards you with gift cards. You can earn $100, $200, even $300 in gift cards every time you use Upside. Plus, you can still get all your miles. Check out Upside.com to see how much you can save by buying your flights and hotel together for one low price. Use the code BIZTRIP, that's Z as in zebra, and you'll receive a gift card of $200 or more on your first trip. Go to Upside.com and plan your itinerary, bundling flights and hotels for a single cost-effective price. And don't forget to enter the code BIZTRIP, BIZTRIP, and be rewarded with savings and gift cards. That's Upside.com. It's not a surprise that the discoveries of these robotic missions elicit surprise. I mean, every spacecraft sets out to accomplish something that's never been done before. But still, as the technology has improved, so has our ability to up our game by going farther and performing ever more stunning feats.
The European Space Agency's Rosetta mission, launched in 2004, was the first to orbit a comet and land on its surface. Like Cassini's eventual demise, 10 years later, the Rosetta spacecraft also met its end by crashing into the object of its study, the comet 67P.
But not before it watched as its lander Philae touched down. Sure, there were some hiccups, says Jonathan Amos, a senior writer and science correspondent for the BBC who has covered the Rosetta mission extensively, but they haven't detracted from a glimpse into how one of the oldest objects in the solar system formed.
Well, Jonathan, we know that Rosetta crashed into 67P, but where is the Philae lander right now?
Well, it's on the surface of the comet as well, not far from where Rosetta came down. If you remember, when Rosetta arrived at comet 67P, it let Philae, the lander, go, and that went down to the surface, and it bounced across the head of this duck-shaped object. If you recall, comet 67P looks a little bit like a duck. And it was the head that the little Philae lander was aimed at. It touched down and then it bounced. It bounced 2 or 3 times, actually, before coming to a stop in a little alcove. And its battery ran down and its solar panels couldn't see the sun, so it couldn't recharge itself. So we only got about 60 hours life out of that little lander. But the great thing was that the mothership Rosetta continued to look for it. And in the weeks before it did its own dive down to the comet, it found the little lander in that alcove, took a picture, and so we know it was safe on the surface, even though it wasn't alive.
The Philae lander sent back data before it fell silent. And John, where are those data now? What have we learned about the comet?
Well, it's in an archive at the European Space Agency. I think they took something like 116,000 images. So that's just pictures. There's all of the spectra from the various instruments as well, thousands and thousands of spectra that will take years, probably decades to get through and to fully understand. And, when they do a mission like that, you're very much in the throes of just doing it day to day. To fly a spacecraft around an irregular object like this with an irregular gravity field, it took a tremendous amount of ingenuity to do that. So once they got through the mission, now is kind of the time when you might expect them to start to pop out the papers. And that's what we're actually seeing now. We're seeing a stream of papers appear in the scientific journals telling us about some of the things that they discovered. So very recently, we had a paper out that showed us some of the surface changes that occurred on the comet while Rosetta was orbiting it. Great cliff falls. You saw cracks appear, and then the boulders rumble down the side of slopes. You saw great outbursts of gas and dust. All of this tells you something about how comets operate, how they're put together. And that is the kind of thing now that we will get from the scientists as they go through all of this data in the coming decades. And I mean decades.
Now, what is it that is attractive to scientists about comets? We want to study them because they've been around since the birth of the solar system, and they might tell us something about those early eons?
Yeah, absolutely. If you look at planet Earth today, it's very difficult to understand or gauge what the early Earth must have been like. And that's because we have an atmosphere and our rocks are continually weathered. We have plate tectonics, which means that the surface of the Earth is constantly recycled. And so it's really difficult on Earth, to find really old rocks, for instance. Most of the rocks that you see on the surface of the Earth, and I include the ocean floor here, are only a few 100 million years old. And yet we know the Earth is 4.6 billion years old. So you go and find those objects in the solar system that haven't been modified very much if you want to learn about the early times. So you go to asteroids and you go to comets. And so by studying a comet like 67P, we kind of understand what the conditions must have been like when the planets and all the other objects in the solar system started to form 4.6 billion years ago. So it's an archive, it's a recording from those times, and it's waiting for us to read.
Well, as someone who covers these missions regularly, as you do, and thinks about the early universe and the early solar system, are you able to get your head around the span of time? You're talking about billions of years. Are you able to get your head around that?
It's a long time, isn't it? Yeah. If I was to pick out one thing from the mission that I think people will kind of consider about the early times in the solar system, when we looked into some of the pits that were on the surface of the comet, you saw how can I describe it? Well, let me describe it how the scientists describe it. It was like goosebumps. When you get really cold, you get these bumps that appear on your arm. Okay. Now, when they looked into the sides of some of the deep pits on the surface of this comet, they could see an effect like that. And they actually called them goosebumps. Sometimes they called them dinosaur eggs as well. If you can imagine a clutch of dinosaur eggs gathered together. It's a sort of bobbly affair, yeah? And they're all about 2 or 3 meters in size. And the thinking is that those are the objects that came together to build that object 4.6 billion years ago.
Well, when you say build, the building, they're coming together. What's bringing them together?
So you can imagine a great big cloud of gas and dust that started to collapse. At the center of it, you would have had the sun form. You'd have also had Jupiter as the other dominant feature in that cloud forming as well. And then, a lot of the dust grains would start to clump together and the ices. You'd eventually have got planets out of that as well, because it would have, formed into a disk around the sun. But further out, you would have got these ices and these dusty grains coming together. And, the theory that they're chucking around at the moment is that you got these lumps that grew to a size of about 2 to 3 meters. These clumps, these goosebumps, then came together themselves to form the larger object that is 67P. And in fact, if you look at the layers as they mapped on the surface of the comet by looking into these pits, you can kind of imagine 2 onions that have come together. Because you see, if you cut through an onion, you see layers, don't you, yeah? Well, it appears that the head of the duck and the body of the duck are like 2 separate onions that have come together because their layers are not disturbed. They're not all completely mixed up. So that tells us that they were probably 2 separate bodies at one time. And then you kind of think, well, hang on a second. They clearly didn't smash into each other. They must have come and touched each other at a very low velocity in order, to maintain all of that structure. So again, that tells you something about what conditions were like 4.6 billion years ago. So now I'm starting to build up a picture of what those early times were like. And, I can then start to think about, well, how did the planets form as well? What sort of processes went into making the Earth, the early Earth? It's all good stuff.
Are you aware of your own avian imagery here, the duck and the goosebumps?
I've had a lot of fun with that. Yes.
Jonathan Amos, thank you so much for speaking with us.
Thank you.
Jonathan Amos is a senior writer and science correspondent for the BBC. Okay, a comet is smaller than a planet, but it can be a storehouse of information, telling us a lot about the early solar system. It's, like never seeing a baby photo of yourself. And then when you find one, you exclaim, oh, so that's what I looked like. The comet 67P grew up in the Kuiper Belt, a swarm of icy bodies orbiting the sun, extending out from just beyond Neptune to way beyond Pluto. And visiting worlds in the Kuiper Belt is just what NASA did recently.
When the New Horizons spacecraft launched in January 2006, it was headed for the 9th planet in the solar system. 7 months later, it was headed for a dwarf planet. The International Astronomical Union's new moniker didn't dim the spirit of exploration one whit for principal investigator Alan Stern, with whom we spoke a year before the NASA spacecraft reached its destination, and for whom Pluto will always be a planet.
New Horizons is the best space mission I've ever been involved in because it's a return to raw reconnaissance. We're the fastest spacecraft ever launched, going farther than any mission ever has, to the very frontier of our solar system, to explore not just a new planet and its satellites, Pluto, but a new kind of planet. This is the first mission to the ice dwarfs of the Kuiper Belt. And what could be more exciting? You know, in the previous generation, the leaders of planetary science in the 60s and 70s and 80s were first to Venus, first to Mars, first to Mercury, first to the giant planets. In this generation, it's very rare to be a part of first-time exploration like this. That's what New Horizons is all about. It's really something like a mission plucked out of the 1960s or 70s in terms of its exploration potential, but done with 21st century technology. What could be better than that?
Mark Showalter, a senior research scientist at the SETI Institute and a member of the New Horizons science team, would agree. Not much is better, except perhaps having the remains of a famous astronomer on board.
We have some of the ashes of Clyde Tombaugh, the astronomer who back in 1930 discovered Pluto. Some of his ashes are actually on the spacecraft.
Clyde Tombaugh would be pleased to be passenger on a journey to the farthest world ever explored by humankind. It's a nice planet if you can spot it, and that New Horizons did. The mission is different from Cassini, which spent 13 years orbiting the Saturnian system. New Horizons, well, blink and you might have missed the flyby. But that close encounter was long enough to collect tons of data, which continue to stream in more than a year later.
And now the spacecraft enters the second part of its mission, mentioned by Dr. Stern, a visit to a Kuiper Belt object. And this is perhaps the most remarkable discovery made by New Horizons. Dwarf planets like Pluto are not oddballs in our solar system, but the main players, and they are plentiful in the Kuiper Belt.
And now, says Dr. Showalter, New Horizons will get a personal peek at one of these main players.
We're going to be flying by a very small Kuiper Belt object, the coldest and oldest object that will ever have been seen up close by a spacecraft. It's maybe 20% further from the sun than Pluto is, and it's just a very small object, but it's a very old and very interesting one, and we'll get our first close-up look at an object from the Kuiper Belt.
Is this sort of Pluto's smaller sibling or something like that? Do you expect it to look something like Pluto?
Actually, probably not. There are many, many Kuiper Belt objects. We know of, I don't know the exact number, hundreds to thousands of them. There are probably, in practice, tens of thousands of them. This one is only distinctive in that it was basically on the path of New Horizons. It was actually discovered just a few years before the Pluto flyby, but that was enough time so that at the flyby, just as we were passing Pluto, a very, very tiny engine burn tweaked the orbit a little bit so that New Horizons is now going to go directly to this object.
Roughly speaking, how close is it to this next target then? Is it, 10% of the way there from Pluto? Is it 90%?
Well, so just the other day, we passed the halfway point in distance. And we are not quite to the halfway point in time. Like anything that is climbing away from the sun, the spacecraft is slowing down as it goes, just a little bit. But that means that we get to the halfway point in distance before we get to the halfway point in time because it's moving a little bit slower now than it was just after it passed Pluto.
So we have something like 1,000 more days before.
That's right.
Okay. So let me ask you this. There was a big team involved in the Pluto mission, the Pluto part of this mission, and now there's a hiatus of on the order of 4 or 5 years between the encounter with Pluto and the encounter with this Kuiper Belt object. What are all these people doing? Are they sitting around, twiddling their thumbs? Are they pumping gas? What are they doing?
I suggest you do a literature search on the topic of Pluto, Seth, and you will find that there are dozens and dozens and dozens of papers coming out, not just from the science team itself, but because our data sets are now becoming public, many other scientists are starting to dig into them and find things that the team hasn't been able to or have time to look at. So we are very, very busy analyzing the Pluto data set. It is an extraordinary data set. And then at the same time, of course, we are getting ready for this flyby. Now, I should mention the most boring name ever used for a target of a NASA spacecraft. It's called MU-69. That's the current official approved name of the target body. We're hoping that NASA will get its act together and give it a more interesting name before we get there. But MU-69 planning is very much underway. We have all kinds of contingencies in store in terms of whether it has satellites, whether it could even have a ring for all we know, dust clouds, whatever. We have to plan for a number of different options because we know so very little about this object.
Okay, so there is a bit of a hiatus, there is an intermission, but the cast has not been sent home.
That's right. We're all very, very busy. And honestly, the Pluto data set is extraordinary, and we're all having the time of our lives just understanding the Pluto system.
Now, let me get back to the spacecraft a little bit. This thing was the fastest rocket that ever was launched by NASA, I believe.
That's right. It crossed the orbit of the moon in about 9 hours, I think. So when you compare that to Apollo, where it took a couple of days to get from Earth to the moon, yes, it was moving very fast.
And very fast means what, about 10 miles a second or something like that?
Well, it did a Jupiter flyby, and that gave it a little bit of extra speed boost. So it's moving along through the solar system at about 14 kilometers per second, maybe 9 or 10 miles per second. So that's pretty darn fast. And it's pretty much traveling at just about that speed. It slows down a little bit as it gets further from the sun. But just for comparison, though, the Voyager spacecraft did flybys of Jupiter and Saturn, and Voyager 2 passed Uranus and Neptune. Each of those flybys gave it a little extra boost, so New Horizons is not moving as fast away from the sun as Voyagers 1 and 2 are, and it will never catch up. The Voyagers are probably going to be the fastest thing we send out of the solar system anytime soon.
And Mark, now, of course, you've been working on the New Horizons project on and off for quite a while now, I think. What is the psychology of this? Because most missions, I mean, you send a mission to Mars, and it gets there in half a year, and you start getting data right away. This took 10 years to get to the primary target. Does that require a different sort of mindset?
Oh, absolutely. And let me just acknowledge that there was a team working on this mission long before I got involved. For as long as we have been from launch to Pluto, you can go back in time before that to the time when Alan Stern and his team were originally proposing and originally designing the mission. Had to go through NASA approval, a lot of missteps along the way where things had to get changed. So the team is extraordinarily dedicated and have been working on this for a very long time. And so, of course, the Pluto flyby itself was a culmination of certainly 20 years of work for some people. And if something had gone wrong at that flyby, that would have been kind of 20 years of work down the drain. So let's really acknowledge the hard work and the really skilled engineers and scientists who put so much time into this project.
Finally, Mark, as you're well aware, there's a bit of a movement, I don't know how serious it is, to reinstate Pluto as a planet. Probably by popular demand. Do you have a dog? I don't know if I can use that term when I speak of Pluto, but do you have a dog in this fight?
I have no personal qualms with the word dwarf planet. When the International Astronomical Union decided to, quote, demote Pluto, they came up with this new term called dwarf planet, and it includes Pluto. It includes some large asteroids, including Ceres and Vesta. It's a pretty strange definition that the International Astronomical Union came up with, in which whether something is a planet or not depends on where it is. So, for example, if you took Earth and moved it far enough away from the sun, it would cease to be a planet. You know, just in our English language, our concept of nouns, the idea that, you know, this microphone I'm speaking into, if I put it somewhere else, it would cease to be a microphone. That's kind of what the IAU definition says. If you took a planet and put it somewhere else, it would no longer be a planet. So the movement is to bring a little bit of more linguistic sense, I think, to the definition of planet, and I'm all for that. I think the idea that there has to be some fixed number of planets that is either 8 or 9 or sometimes 10 is really very silly. We certainly all understand that there are big rivers and medium-sized rivers and small rivers. Why can't there be big planets and medium-sized planets and small planets? And planet's just kind of the generic term in my mind, and I hope eventually the International Astronomical Union comes to see it that way as well.
Sounds like there's reason to be optimistic, at least for the smaller members of the solar system. Mark Showalter, thanks so very much for talking with us.
It's been a pleasure, Seth.
Mark Showalter is a senior research scientist at the SETI Institute and a member of the New Horizons science team. And he and his colleagues, by the way, discovered 2 of Pluto's 5 moons, Kerberos and Styx.
As New Horizons approaches the Kuiper Belt object MU-69, we'll learn more about these icy bodies, Pluto's buddies, and the most common type of object in the solar system. But regarding Pluto itself, well, the mission has discovered evidence of liquid water beneath its surface. So we are finding that, just as in the case with Saturn's moons, even the most inhospitable-seeming worlds have liquid water.
Well, there are lots of firsts in these solar system missions. Here's another. The first spacecraft to leave the solar system and venture into interstellar space, and the pioneering rock and roller along for the ride. Plus, the answer to the riddle, why did the rover climb the mountain?
It's Spacecraft Elegy on Big Picture Science. We're taking a look in this program at some historic spacecraft, where they are now and what we've learned from them. But one continuing mission wins on longevity alone, the twin Voyager spacecraft. Yes, Voyager 1 and Voyager 2, they're still going, still occasionally sending back data, earning the title of NASA's longest-running space mission. California Institute of Technology physicist Ed Stone was the project manager of the mission when it launched in 1977.
A few years ago, he reminded us of the special cargo that Voyager carries.
We asked Carl Sagan to set up a committee to design some sort of message from Earth. The Pioneer spacecraft had plaques, but the committee decided it would be nice to actually have a record. Now, this is an analog grooved record, but nevertheless it has on it images of Earth. So it obviously has pictures of humans, but it also has pictures of nature. It has sounds of nature. It has music from around the world. It has many different languages, greetings in many different languages. So it's an attempt to send a picture, if you like, of the planet, which in fact for the first time could reach out and leave its own solar system.
That record is the most famous part of the mission. One of the pieces of music is Johnny Be Good by Chuck Berry, who recently passed away at the age of 90.
I have a connection to that song, Seth.
You like it? I like it too.
It's not just that I like it. Johnny Be Good supposedly is my great uncle, John Barlow Good.
Really?
Yeah, and so the song Johnny Be Good was written about him.
Did he give you any sheet music as an inheritance?
No. But this is information that's been passed down through the family, and if there's anyone out there that has other information as to the identity of Johnny Be Good, I'd be very interested, but I believe that was my grandfather's brother. I
wish I could make a similar claim. You know, there was one guy who got 2 pieces of music on that record, that Voyager record. That was Ludwig von Beethoven. I am told by Frank Drake that the various committees to decide what to put on the record mostly got along with one another. You know, which art should we put on, which photos, what, statements from world leaders, how do you say hello in 47 different languages, whatever it was. But the one committee that really got into a fight was the music committee. They were fighting tooth and nail, according to Frank.
But this gets to the purpose of this. Was this a publicity maneuver by the managers of Voyager, or was the idea that one day maybe aliens really would hear this music?
Yeah, there certainly is the possibility that aliens might pick it up, but I kind of worked it out. It's going to get within a light year of some star system after, 50,000 years or something like that. And the chances that anybody will find it would be like the Hawaiians finding a speck the size of a bacterium in the Pacific Ocean. So I doubt it'll ever get picked up. It was mostly to go through the exercise of figuring out what would we ever say to extraterrestrial intelligence.
Okay, so this record and these spacecraft are traveling through the bitter cold of interstellar space now, I believe, right?
They are.
How much longer?
Forever. I mean, unless they hit something. Yeah, unless they hit something. Mind you, things will break and micrometeorites will sand away the record. I mean, it's not going to be a record you'll be able to play forever, but the spacecraft will it'll just keep going.
Wait, you're saying that the record may deteriorate, but the spacecraft will literally keep traveling forever?
Yeah, it's like your car. If you just park it in the garage, how long is it going to stay there?
No, that's not like a car. A car doesn't stick around forever. I mean, literally, these spacecraft will travel through space forever, till the end of time, till the end of the universe?
Maybe, yeah. Look, there's no weather in space, right? Eventually, if you talk about infinite length of time, eventually they'll crash into a star. How's that?
So their exit is a slow, gradual
They just go away.
Absorption into the recesses of space.
Yeah, you could look at them as the tombstone of humanity because it'll be there a lot longer than the Earth will, or certainly than we will. Voyager is perhaps our best tombstone because it will last so long.
Well, from the spacecraft that are the furthest away from the sun, we finish our tour of the solar system missions with something a little closer to home.
I'm Ashwin Vasavada. I'm the Curiosity project scientist, and I help lead the international team of scientists who every day comes together to figure out what the rover's going to do on Mars.
NASA's Curiosity rover is the one that landed on our little ruddy buddy in a very elaborate sequence of events. You may remember a streamlined capsule holding the rover, first penetrating the Martian airspace, and then a parachute slows it down till it's pretty close to the surface when some cool retro jets fire up and lower the rover by wire rope, before speeding away. Curiosity settles down on the surface of Mars to begin its mission. Now, that was in 2012.
Well, it's still there now, building on missions that came before it. You remember, of course, Spirit and Opportunity. And in doing so, Curiosity may deliver the most tantalizing data yet from Mars. Now, we know that Mars had liquid water at one time on its surface, but for when and for how long? Well, to answer that, Curiosity is climbing the sedimentary rock that makes up Mount Sharp.
This mountain is about 5 kilometers or 3 miles high, and it's one of the larger peaks on Mars, especially considering it's inside of an impact crater. And that really is what drew us to this site, because that mountain didn't form with the crater. It actually formed when wind and water brought in sediment to that crater. So, considering that way of forming, it's a big mountain of layered rock.
Okay, and why is Curiosity climbing this mountain? I mean, not because it's there, presumably. There's some reason that NASA spent a lot of time, a lot of money to send a motorized robot to climb a mountain.
Yeah, our mission for the last 5 years has been to figure out if Mars ever had the conditions for supporting life. And we were able to determine that early in the mission when we found a lake, evidence of an ancient lake, out on the plains surrounding this mountain. But then as we got closer to the mountain, we really wanted to figure out if it formed by water or wind or some combination of both. So now that we've been climbing this mountain, the layers that are preserved there have told us, just by reading the geology of those layers, we can figure out that water was involved. And in fact, every layer of the lower part of that mountain was once mud at the bottom of an ancient lake.
So, in fact, what you're looking at is a kind of a layer-caked history of water on Mars.
That's right. Water on Mars is something that is central to NASA's exploration of Mars because it's such a key component for life. But we can do a lot more than that. Curiosity is a car-sized rover because it carries a drill and laboratories that can analyze sediment that we drill into and deliver to those labs. So not only can we tell that there was water there, but we can tell the chemistry of that water, that the water was generally fresh, didn't have too much salt dissolved in it, wasn't too acidic, and had a lot of the nutrients and chemicals that life requires.
So if I'm getting this correctly, what you're finding is that Mars once had at least lakes, maybe oceans, on its surface of fresh water. That sounds like the situation that might lead to life, indeed. So is Curiosity going to dig into the mud there, or the ancient mud, I guess I should say, and actually look for, fossilized life? Is that on its agenda?
That is really what the next Mars rover is set to do, and we are setting the stage for that by doing the analysis of the habitable conditions. Were all the environmental conditions right to create long-lived liquid water? Were all those nutrients and chemicals available for life? And then, you can only do so much with the instruments that you brought with you. And we're optimized to do that kind of study. And the next rover, Mars 2020, has a payload that's dedicated to actually finding traces of life.
So it's on reconnaissance for places for a follow-up rover to actually look for evidence of biology.
That's correct.
Okay, now, look, I don't climb mountains for a living or even as a hobby, but I've seen the photos, I've seen the movies, and, they've got funny boots and pitons and, axes and stuff like that. I assume that this rover doesn't have any of that stuff. How can it climb this mountain? It's just a little cart.
That's right. It's a 6-wheeled off-road vehicle, so it's pretty capable that way. But fortunately, also, the mountain isn't a vertical face. Amazingly, without any road building on Mars, we've been able to find paths up the mountain using the incredible images we have from the satellites that we've had mapping Mars for more than a decade. So we can actually chart a path from the plains around the mountain up through the mountain, finding every little canyon and every little place where there's an accessible path for our rover.
All right, so at this rate, are you going to go all the way to the top with the rover? Is it going to, summit this mountain?
No, that's not really the plan. We really want to focus on the very lowest part of this mountain, the foothills, if you will, where all this really intriguing evidence is from orbit. We can see clay minerals, for example, from orbit, and we're driving to one of these regions right now, and clay minerals occur when rock interacts with water over a long period of time. We're going to little spots on the treasure map that we've created from the satellite imagery, and trying to reach each of those areas, as long as the rover survives.
Order of magnitude, how old are those deposits that you're digging around?
All the geology that we're looking at probably dates from about 3 billion years ago. And that's right at the end of the period that most scientists think that Mars was at least wet with a lot of liquid water, if not also warm. And so we're right at the end of that period when Mars is transitioning into a colder planet and a dry planet like it is today. So it's pretty exciting not just to see that evidence of the liquid water, but also to maybe see a glimpse of how Mars changed so radically to dry and cold.
So, it's conceivable and maybe something to hope for that the rover is rolling across the burial plots of microbes from 3 billion years ago.
That's right. That's when we think Mars had the best chance for supporting life. And so we're really excited to be in the kind of a geological wonderland that dates from that time period.
And finally, Ashwin, the Curiosity rover is not the only spacecraft we've got out there, or it's one of the few rovers, I guess, now, but it's not the only probe we've sent into the solar system. We have the Cassini mission and the New Horizons mission and spacecraft that have been out there for decades. How would you say that the Curiosity mission complements the other exploration of the solar system by spacecraft? And how could a discovery on Mount Sharp, such as you've been describing here, change our understanding of the history of where we live?
Yeah, NASA has an overall goal for planetary exploration of understanding whether life exists outside of Earth. And, we don't really know. We have a limited understanding of where the best places for that might have been in the solar system or are today. So, I think it's great that NASA is able to explore the ocean worlds of Jupiter and Saturn's moons, and then also go to a place like Mars, which may not have life today, but may have had abundant water on the surface, very much an Earth-like situation 3 billion years ago. So all these spacecraft work together to answer this very fundamental question of, did life ever originate or exist in the solar system outside of Earth?
Ashwin Vasavada, thanks so very much for speaking with us.
Absolutely. It's been fun.
Ashwin Vasavada is the Curiosity Project scientist at the Jet Propulsion Laboratory in Pasadena. Well, so what we're seeing in this show is that these rovers, flybys, and other spacecraft have changed our understanding of the solar system.
Well, they have. And, what were only, kind of faceless dots in the astronomy textbooks when I was a kid have all developed personalities. I mean, the moons of Jupiter, Saturn, we didn't even know about most of them to begin with. And now we see that they each have interesting terrain, history, and possibly even liquid water.
And in fact, we're finding that even the most inhospitable bodies in the solar system have water. That has come as a surprise. Enceladus is one, Titan is another, and even water on Pluto, possibly.
Yeah, well, underneath. That's right. So you can't call them inhospitable anymore. If they've got liquid water, maybe they are hospitable. Maybe they've even got life there.
Right, so that raises the question of where else in the solar system there might be life. And now there are a few candidates to search for that life. Mars is certainly one of them, ongoing, and but also Enceladus.
Yeah, well, Enceladus may be one of the best candidates, but Europa, really, there are a half dozen. But the other thing that all of this has taught us is that the big planets of the inner solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, we always thought they ruled the roost, but in fact the roost is ruled by these dwarf icy worlds of the Kuiper Belt. Hundreds of them. They greatly outnumber these iconic planets.
And then the idea that for a picture of our early solar system, you look to some of the smallest members in it, the comets. And the comets hold the secret to how the solar system may have come together, but also the bodies within it.
The comets and the asteroids, yeah, because they've been in a deep freeze for 4.5 billion years, sort of time capsules, although they probably didn't sign up for that. That's what they are because they haven't been affected by weather or tectonic activity or any of that stuff. They're just sitting there waiting for us to explore them and to learn their secrets.
So we say goodbye to these spacecraft, but the discoveries stay with us.
Yes, that's true, at least as long as they're humans. But you know what? Some of those spacecraft will live longer than the discoveries.
Well, thanks to those who voyage with us each week to make this show, senior producer Gary Niederhoff and operations manager Barbara Vance.
Thanks also to financial support from Rena Shulsky-David and Sammy David and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including understanding how rings and planets form. And a big thanks also to our listeners.
Your ears have been attuned to the Big Picture Science episode, Spacecraft Elegy. If you'd like to hear more Big Picture Science episodes, well, you'll find them in our archive at bigpicturescience.org.
And if you're a podcast listener but prefer listening to over-the-air radio because of some peculiarity in your upbringing, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show. And to reach us directly with your comments, throw in some faint praise, and then email it all to bigpicturescience@seti.org.